Okay, we're doing a lab evaluation of data. It's been a little while since I've recorded one of these videos. This is for the accelerating cart lab. So first of all, let's take a look at the graphs. Hopefully you haven't printed out. We've got three relationships we were trying to figure out: position in time, velocity in time, and velocity in position. So that was our purpose of this lab, to do those three equations. So I'm going to kind of do them simultaneously across the paper here, write it up, I'll scan it and get it to you. So we had, let me just do this. We had position versus time. We had velocity versus time. And we had position or velocity versus position. Now, hopefully you can see that pen well enough. I'll scan it. A little bit of a mistake here. That was velocity versus position. Now, keep in mind, the Logger Pro calls the V X velocity. We didn't care about the blue data, the Y. So first thing we did was we looked at the relationships, and we saw that position and time were not directly related. In fact, they were curved, right? It looked like this to start off with. Let me ditch these papers underneath. We saw position versus time, X versus T. We saw a top opening parabola. So we squared the time values. I just told you guys to do that. And we saw it became linear. We call that linearization. Velocity and time was linear right out of the gate. We didn't have to do anything. Velocity and position was nonlinear. It was a side opening parabola. Top opening, side opening. Top opening and side opening. All right, and that was velocity and position. And what we did for that one was we squared the velocity values and we got a straight linear relationship. All right, so then we recorded the experimental equations. All right, so the experimental equations come from your data. So for this one, it's x equals, we put the number in, 0.61 meters per second squared times t squared plus 0.029 meters there. So that's our experimental equation for position and time. It was position was directly related to time squared. For velocity and time now, we have V equals, and this is my example one I had done in class. This is my data set. So your numbers are going to be whatever shows up in the here from your fit line, the slope with units, the slope with units, the slope with units, the y-intercepts with units, and so on. So the slope of this one was 1.05. I only did 2 sig figs here, so I should probably stick with that. 1.0 meters per second times t plus 0.03 meters per second. This one here now was, let me move this up for a second. It's velocity squared. The units are kind of strange. The y-intercept has got those kind of a same strange units. So the equation ends up being v squared equals 2.1 times position x, oops, I forgot the units, 2.1. Oh, that's a big blunder because I need some white out to fix this. 2.1, and it's, I'm gonna put the units down here. It's gonna be meters per second squared per meter, which I'll show the simplification of that, times x plus 0.018 meters per second, and then the whole thing squared. All right. Then we talked about the meaning of the slope and y-intercept. All right, so let's take a look at the y-intercept first. For each of these, we've got a y-intercept. All right, kind of draw little arrows here. The units are meters. All right, so that would be the position when time squared equals 0. Time squared equals 0 would be 0 seconds. So this is the initial position, we call it. Call this the initial position. Symbol is going to be an X with a little I. All right. Initial position, the initial coordinate along its motion. So the slope then has units of, it says meters per second squared, because we squared time. So rise over run is you go up a certain number of meters over a certain number of seconds squared. Okay, I have no clue what that means. It's the rate of change of the position relative. No idea. So let me go to the next graph. I'm going to come back to this. All right. This next graph, velocity versus time, the y-intercept is going to be the initial position. All right. The units are, or initial velocity, I'm sorry. The units are meters per second. So I'm just going to get right to the punchline. The initial velocity, the symbol is v initial. It's the velocity when time is 0. So it's the velocity when you first start moving. Now the slope of this line, this is the big one. The slope of this one is meters per second per second. So it's how much the velocity changes each second. We call this acceleration. All right, and the symbol is an A. So lowercase a. The units are meters per second each second. So this is a new definition. This is really important, right? Acceleration. It's the rate of change of velocity. That's another way to say it. How much velocity changes each second. The rate of change of velocity. All right. Okay, so that one's done. Does that help us out here? Well, look at the units, meters per second, and meters per second squared. Okay, so meter per second, you could actually write that a little bit different. I'll do it down here. Meter per second, all right? So that unit. If I wanted to convert this to a more compact unit, what I would do is I would do meters per second times 1 over seconds, right? When you divide a fraction, whatever's on the bottom, you invert it and then multiply by it. So that would actually bring us to the same unit as the first one, meter per second squared. Meter times second over second times second. So that unit is equivalent to meters per second squared. So meters per second squared is also units of rate of change of velocity, but the numbers aren't the same. This is 0.61, this is 1. So it looks like acceleration. So I'm going to write that here for now. Looks like acceleration. But it can't literally be the acceleration because the number's not the same. So let's go over to the last graph and see if we can figure it out. This one here, the y-intercept, is meters per second squared, which is simply the initial velocity squared. If you square that, you should get something close to this, but yeah, it's not quite, right? 0.03 squared, I don't know what that gives. So this should be the initial velocity, but squared. So VI squared. The slope of this one, all right, we're gonna have to do some work here with this unit. The units, which I poorly wrote up there, is meters per second squared per meter. Okay, don't know what that is, so let me see if I can condense that down a little bit. So let's see, meters squared per second. Let's deal with that first. If you square that, it's meters squared per second squared per meter, which then gives us one of the meters cancels and we end up at meters per second squared. So this one also ends up looks like acceleration. All right, it ends up looking like acceleration as well because it also has units of meters per second squared or meters per second. So now we got to figure out, okay, these all look like acceleration. All these slopes look like accelerations. They all have something to do with acceleration. Well, what it is this one, this slope was A. If you look at the numbers, this was actually 1.05 if I went to 3 sig figs. Twice of 1.05 is 2.1. So this slope is actually twice the acceleration, right? And you can check it, and you should in your write-up. So this slope is 2a. So the y-intercept is v initial squared. The slope is 2a. If this one's 2a, then look, this one's 0.61. It's not great, but that should come out to be about half of the slope of this one. So this one ends up being actually 1/2 a. It's about 1/2 a. If you did this experiment again, you might get a better result. All right. So that's the evaluation of data, right? This is accelerating CART lab eval of data. All right, I figured out each equation, experimental equation with units. It's directly proportional, position is directly proportional to time squared, velocity is directly proportional to time, velocity squared is directly proportional to position. And the final thing we have to do is the general equations, we call these, right? The final general equations, right? I could kind of make a line here, kind of separate these three a little bit. The final general equation, this is where you put the variables back in. So the general equation, all right, you put the variables that we just derived back in there for the numbers. So x equals 1/2 the acceleration times time squared plus x initial. This one is v equals at plus v initial. And then this one, plugging back in 2a for the number, we get v squared equals 2a times x plus v initial squared. So these variables, keep in mind, this could be final, x final, v final squared. It's the position at a later time, the velocity at a later time, and the velocity squared at a later position. So those are your general equations. Lots of possible sources of error in this lab. I'll let you come up with those. Things you could improve. There's things you could do there for sure. So hopefully this helps you write up your lab. I'll be posting this ASAP.